Great. Yeah. So great to be here virtually with you all. So I'm going to talk a little bit about really the main focus of the research group that we have at Goldman, which is on, what do we have to do to get to quantum advantage in finance? Like, how do we make money with these things? And I'll spotlight a little bit that two things that are pretty key are error mitigation and fault tolerance. So a little bit about our group. So, why does a bank care about quantum computing, and how do we think about it? So our approach is to try and work backwards from well-defined mathematical problems that matter in financial services. So luckily in finance, there are some things about it that make it appealing for trying to apply any kind of new computing technology. You have problems where a technical improvement, doing something a few percent better, can be linked to business value relatively quickly. And if you have better computers, you can deploy them at scale very, very quickly as well. The downside of financial problems is that they're not obviously quantum. There's not obviously quantum data floating around. But anyway, our approach is to work backwards. So we take these problems, they're well benchmarked, and ask what are the quantum resources needed to get to advantage, and as much as we can, try to think about the constant factors as well. So there's really three parts to this. So one is the resource estimation. The second is the algorithm design part. So taking algorithms and trying to optimize them for our setting. And thirdly, the part that is especially relevant to this workshop is integrating with hardware and roadmaps. We're not building hardware internally, but we try and talk with all the different groups and to understand not just where they are now, where their architectures could be. We don't want folks to spend a lot of time and money and energy in building something that 10 years from now we know is not going to have specs to do useful problems. And we collaborate with a bunch of different folks. So this talk is going to have sort of two sections. I'll talk first about financial applications, where this working backwards approach usually is about things that have provable advantage, and this often leads us to resources big enough to definitely need fault tolerance. I'll talk about two applications, one derivatives, one in something called calculating Greeks. I'll talk a little bit about input estimation. Then I'll talk about sort of shift gears a little bit to the second bit to think about error mitigation itself. So there's kind of two bits to the talk. One is applications-ish. The second is not explicitly hardware, but closer error mitigation, firmware-ish layer. So hence the combo for co-design. And if you were here for Sergey's talk just before me, he covered some of the stuff that's in error mitigation too. So I won't double cover, but you'll see the resonance. So this first part. So I like to think about this resource estimation problem as being simplified to exist on this landscape of quantum power, at least. There's more dimensions to thinking about specs of a quantum computer, but we can start with these. X-axis, we have the number of qubits available to a programmer, and then the depth, broadly speaking, on the y-axis. And so these equipotential lines are at your error rates, right? 10 to the minus 3, 1,000 gates on 1 qubit, or 1 gate on 1,000. So a bunch of things. Where are we as a field here? I mean, and this is an artist's rendering plot here. There's some fuzziness. You can move things around, but just to kind of broadly anchor, things start to become not obviously simulable by classical computers once you're in this sort of regime, and hardware is kind of around here today, but it's a moving target. So from a resource estimation perspective with applications, our goal is to put target applications on this plot as well. And so one thing we did is take a look at a problem in derivative pricing. I'll talk about what that is in a few minutes. At its core, it's amplitude estimation. So there's a theoretical speed up there, but we needed to work out the constant factors and also have a benchmark classical problem that's really, relatively speaking, the state of the art classically. And then, well, in both of these, we had collaborators at IBM. We extended that to an application in Greeks, which sits around here on the plot. And so there's a little bit of a gap here, as you can see. The other thing I'll just mention is that there's really a third dimension that matters a ton, and it comes up in this application as well, which is what's the clock rate of your quantum computer. And in these resource estimates, we're really thinking about the rate at which you can do T-gates. But broadly speaking, it's what's your clock rate in general. And so you might say that derivative pricing is, it seems to be easier than Shor's in terms of finding advantage if you're comparing to 2056-bit decryption using Shor's. But it has a pretty high requirement on the clock rate. So you need to be able to do T-gates that are around 50 megahertz, which is, I think, probably the scariest of the resource requirements here. So the Greek application requires a bit less qubits, maybe about the same number of operations, but you can go slower, which is nice. I kind of joke that the way to think about what our research group is trying to do is we're trying to put dots on this plot and move them down and to the left. Easier said than done. So let's dive into, I'm just gonna adjust my audience view here. So let's dive into this first application of derivative pricing. And at the end of the day, we're going to leverage a quadratic speedup on calculating the expectation value of different functions of stochastic processes. So that's what it means, but maybe I'll give you like a high level summary. Like the financial use case is, I want to sell you a contract today that gives you the right a year from now to buy Apple stock at $200 a share. And maybe Apple today is at $100 a share. So what is that contract worth? Like, how much should you pay for that contract today, given that it just gives you an option to do something in the future? And the way you value that contract today depends on how you think the price of the underlying, as we call it, the Apple stock, is going to change over the next year. So like, if you think the Apple stock is going to be very volatile and move up and down a whole ton, it's very likely to maybe double, have which is what you need for you to want to take that option. But if you don't think it's going to move at all and it's going to stay around 100, you wouldn't pay very much. So anyway, that's kind of these things are ubiquitous in finance. There's trillions and trillions of dollars of these that are traded all the time. It's an enormous market. So being able to price them quickly, they get complicated, is important. So mathematically, what's going on is we've got some vector of real numbers, like these are stock prices. Let's say they're D different stock prices at some different set of times T. And then we're going to define some model for how we think those stock prices are going to change between time T equals 0 and time T equals big T, so like a year from now. And each one of those possible paths that all those stock prices could take has some probability associated with it, given our model. So importantly, this is not backward looking. Like, we're not looking at historical data. Maybe our model is informed by historical data, but what we're doing with the stochastic process is modeling it forwards. And so, like, being physicists, we could say, let's start with Brownian motion, and like that back in the 60s and 70s, that was a place to start. So you might have, this is maybe one set of paths for 3 different assets. And so like this trajectory, maybe these assets started all at $2 and then they move over time. Each one occurs with some probability. So then the next component we need something called a payoff function. And this tells us how much money the contract that we might buy might make us if some particular path is realized. So like in the example I gave before, which is something called the European option, then if I have the option, if let's say my stock is at $2 today and I have the right to buy it at $2.10, then that's not worth anything if the green path or the blue path is taken, because why would I want to buy it at $2.10 when it's 190 or 180? But it is worth something if the orange path occurs, because the orange path is maybe at like 215. And so if I have the right to buy it at 210, I can buy it at 210, sell it at 215 right away and pocket the difference. Mathematically, you just need to have some kind of function from each path into some amount of money that you make. And so then to figure out the value of that contract today, you're just going to weight each of those payoffs by the probability of that payoff occurring, or the probability of that path occurring, and take the expected value. And that's how you price them. And so that's what this is here. In the example I was speaking about, there's some strike price. Let's say that's the $2.10. You're either going to make zero, which is if the path goes, underneath that strike price, or you're going to make the difference if it goes above that strike price. So anyway, it's just an expectation value. Oh, and you can do this with there's a bunch of different methods for doing this, which I'll speak about in a minute. So importantly, this example that I've given you, where you just look at time big T to see what all you need to know in order to calculate the payoff is to look at time S of big T. Those are called path independent options. And the reason is that you actually don't care about the path between time T equals 0 and time T equals big T. You just care about the value at the end. So the path to get there doesn't matter. And often those are easy to price. So this thing called the Black-Scholes model, which is pretty famous, applied originally to certain kinds of simple stochastic processes, and also to path independent options. And so they're actually, for a lot of path independent options, there's analytical formulas for doing this under a bunch of different kinds of stochastic processes that you might have. So it's very important when we think about applying a quantum advantage to this problem that we focus on things that are not already easy. And so here that means we need to focus on things that are called path dependent derivatives. And just to give you a flavor of some of these examples, you can have payoffs where you make some amount of money if at any point the price goes above some barrier, but not below some other barrier in the second half. So you can get kind of these like complicated logics, or you can have payoffs where you care about the average price over the time window, not the final price, or you maybe care about the realized volatility of the walk that the path takes. It can get sort of involved. And for the more involved ones, the best method is like a high dimensional Monte Carlo integral. So which just means you run each path. You have a stochastic model, you like stochastically sample each path and compute the probabilities. So what we needed to do an estimate for where you could have a quantum advantage was to start with the core. You need to start with some core theoretical advantage. And using amplitude estimation, Ashley Montanaro showed that this can fit well into a speed up of pretty generic Monte Carlo methods back in 2015. And the difference is that when you do this classically, you get a scaling of 1 over epsilon squared. So if you want to get this expectation value to epsilon, then that's the number of oracle calls you need to make or paths you need to sample. And the quantum scaling is 1 over epsilon, so usual amplitude estimation stuff. But to figure out the constant factors, we had to pick some specific examples. And so we picked two. One's something called an autocallable that comes from stocks, and the other is called TARFs, which comes from contracts on currencies. I'll just refer you to the paper, but they got like kind of like some fun structure to them. But we really implemented the oracles. We estimated their size, calculated the T count, had a target error rate that we wanted. In this case, I've got 2 times 10 to the minus 3. And we're able to estimate that you'd need a T count. Well, there's a few things that are interesting about this. One is that you need 1.2 times 10 to the 10 T count, maybe 8,000 logical qubits. So this is definitely in the fault tolerant regime. But it's maybe not as big as you would think. It's only a quadratic speed up, not an exponential speed up, but it's, the raw constant factors are less than Shor's, for example. The other takeaway is that we took the kind of basic implementation of how you would think about doing this from the literature, which is kind of this Riemannian sum method, and started to do the constant factor estimates there, and they are intimidating. Around something like 10 to the 43 we sort of stopped once we knew that was the base estimate. And so we had to introduce some tricks. And the tricks here were figuring out how to load this stochastic process into quantum memory in a way that wasn't really horrendous in terms of constant factors. So it's known by Grover Rudolph that you can load this efficiently, but the constant factors are really bad, and so we had to add some new tricks to do that. And incidentally, I actually had a blog post about a month ago where these were by hand estimates. We now have a Q# implementation where we refine these a little bit more. All right, so we're on time. Great. So now I want to tell you a little bit about the second application that we looked at, or at least that we published about, which are calculating market risk. These things are for historical reasons called Greeks. And so what they are gradients of expectation values of functions of stochastic processes. So I'm not going to call them derivatives because then you get like a double, there's degeneracy in the word derivative here. But so recall the derivative price is just a weighted average of the payoffs for each path. And then if we want to know how this price is going to change with respect to model parameters, market parameters, we want to know basically its sensitivities. So that's going to be a set of gradients. Let's say there's k different parameters that we care about that we want to take the derivative of this price with respect to. And often you want to do this because you want to hedge the risk of holding that position. So that means that, maybe I found out that this contract, I think it's worth $100. But it's on if the volatility, if the rate that the Apple stock moves, if I've estimated that poorly, then it's not worth $100. It's worth $0. Then I want to act differently than if I estimated it poorly and it's only worth 99 instead of 100. So you treat the risk of buying that contract differently. So an example is something called the delta, which for a single underlying stock is the rate at which the price of the derivative contract changes in the underlying price. So if the price of Apple stock goes up by some amount, how does the price of the derivative on top of that change? So in this case, we've got sort of a k-dimensional gradient. So how would you do this? So one method, basically you need some combination of, you need to do Monte Carlo plus a gradient algorithm. So one way is you can use classical finite difference. So you get 1/epsilon² scaling for each pricing, and you're going to do finite difference in each dimension. You're going to do 2 pricings, and so you have k, of order k of those, and so you'll get k/epsilon³. There's a somewhat better method using something called common random numbers with sharing randomness in how you do each of the pricings, which will give you k/epsilon². There's what you could call a semi-classical method, which I think that terminology I've seen first in this Gillian et al. Paper from 2019. And so here what you do is you do finite difference, but every time you do a pricing, you use the quantum version of the Monte Carlo integration. So that will scale as k/epsilon. But you might ask, can you use some quantum gradient algorithms to improve the scaling with k as well? And the answer is yes, but a little bit subtle. And so just a kind of a short reminder on quantum gradient algorithms. So broadly, the sort of trick here is a combination of a phase oracle and the quantum Fourier transform. So let's say we've got some function from r to the k to r. Jordan showed in 2005 that if you're given some point x that you want to take the gradient around and some s, then you want to start with some oracle like this. Then what you do is you can evaluate this oracle in a k-dimensional hypercube of n different points. So basically take x and in every dimension move by delta. Sorry, the set of points that you want is delta and move by a spacing of L all centered around x0. And then you want to evaluate the function on all of those points in superposition. So this is, in one dimension, it's just sort of like finite difference, right? In one dimension, you have the point you're starting with and you move in both directions. So we'd be summing over those 2 different directions. That would be delta. And then we want to apply this oracle to each of those points. And if you do that, then you can assume, if this spacing L is small enough that the function is locally linear around that point. And so I can replace f of x plus some small amount delta with the gradient of f there times some small amount. And pull out just the value at f of x0 just becomes this phase you can pull out of the sum. And this looks like a hidden shift problem, so we can do the quantum Fourier transform to pull out this gradient. So this looks like it will work, but the error scaling matters a lot. So if you follow through this in detail, then you do get a square root of k scaling, but you find that your value s here needs to go like n over L, which ends up meaning that you have an algorithm that scales as square root of k, not over epsilon, but square root of k over epsilon squared. In 2019, Gillian et al. Took an approach to try and fix this and do by introducing some higher order oracles. So not just thinking about an oracle that looks like this, but let's look at the first order one. So instead looking at an oracle that evaluates not just f of x, but f of x and f of minus x, like around the point. And you can move this up to some nth order where there's these terms to basically higher order finite difference formulas that you can use. So if you do that, then they prove that choosing an m that is log of square root of k over epsilon, where c is some factor that depends on the smoothness of your function, then that's sufficient to achieve the scaling that we want with some other terms in here, but basically square root of k over epsilon. So this works great from a theoretical perspective, but building a circuit to do this is fairly sophisticated. And they suggest that you should build up this this higher order term, which could get kind of big by using some kind of block encoding or quantum simulating value transform. And so one thing that I like to say about this is that you might think that quantum Hamiltonian simulation is not relevant for finance, but like it's very, it's definitely relevant. It's also relevant through HHL and linear systems and other things like that. But this part right here can be very expensive in terms of resources, even though it scales nicely. So this should appear later. Maybe I'll just do this. So in our work, we wanted to take a look at what the constant factors were actually going to be, and that involved also looking not just at the theoretical bounds, but also the sort of numerically how well this algorithm worked. And we couldn't do this on too big of an example, just because of how things scale. But we took a relatively practical example. So we took an example of a four-dimensional Greek. So four different Greeks on something called a basket option with a knock-in. So this is a multi-asset option. So we have multiple stocks, and it only it pays off some weighted. So we have some weight here. We take some weighted average of the stock prices, compare them to some strike, and that's how we'll determine what our payoff is. But then also this only pays off if at some point the weighted average of the stocks is above some threshold value B that happens. So anyway, we pick some parameters that matter in our domain, and there's not an analytic. Basket options don't have a nice easy way to price them analytically, even under simple stochastic processes. And so really the thing we had to compare against is classic Monte Carlo. So we looked at a bunch of the different algorithms that I discussed and compared them. So if you do this with classical finite difference, the number of oracle, and we did this in terms of oracle calls. The number of oracle calls you need is about 400K. Common random numbers reduces it by more. if you, the semi-classical method that I mentioned, where you just do pricing classically, pricing quantumly, but use classical finite difference, actually performs really well. And if you were to compare the semi-classical with this GAW is the Gillian approach, just what you would get from looking at the theoretical bounds in that work, then you'd say, this was even worse than classical finite difference with common random numbers. Numerically, it performs a lot better, but still, the semi-classical method looked to perform better than the Gillian method if we do this block encoding construction. And so we introduced a specific construction for the the sort of m equals 1, which is, I guess, the second order, because it's 0 indexed, the second order finite difference formula, which dropped this by quite a bit and finally beat the semi-classical method. So I think one other kind of takeaway from this is that, which I think a lot of people know, is that there's just a big difference between how computational complexity scales and how things will compare once you start to look at constant factors, even on small instances. Like this is a relatively small instance. So if you just looked at theory and scaling, you would probably assume that semi-classical is the best way to go. Oops, what else do I want to say here? Oh, yeah, and the main cost is to this one is still Hamiltonian simulation, so we care about that. So to sum that up a little bit, we needed something like these resources to using the reparameterization method to do one pricing, and that we need to do in a second. Greeks, we have some more time for. It's a little slower classically, so let's say we want to target of order 10 seconds. Then that means that the target QPU clock rate is now 7 megahertz for T-gates instead of 50. Again, it's quite a demanding thing to ask from hardware roadmaps today, but maybe we'll be able to keep, I think, not maybe, I'm pretty sure we're going to be able to keep lowering this. And in particular, if the theoretical bounds remain loose as we get to much larger numbers of K, then the advantage will increase a lot more favorably, but we haven't yet been able to analyze that just numerically. Great. Time. And so that kind of leads us to seeing that, like, here's a couple example applications that we published about that are over here, and the hardware's over here. So what are the kinds of things that are going to help us in between? And fault tolerance is definitely a really, really big one. But we also want to think about error mitigation and other kinds of algorithmic tricks. So one thing I want to talk, maybe I'll keep this section over briefly about, is some work we've been doing on the key subroutine for these kinds of pricing and risk algorithms. And this is sort of introducing some tweaks to how amplitude estimation works, hopefully to make it be a better benchmark for tracking as progress towards really, really practical amplitude estimation algorithms. So the idea here is something we call like low depth amplitude estimation. And the idea here is that normal amplitude estimation requires it's kind of all or nothing. You have to run at a depth sufficient to run the algorithm. And if you do, then you get a full quadratic advantage. And maybe there's some way that we can have a sort of slowly turn on that advantage as we can run longer and longer circuits. That's the idea. Right, so normal Monte Carlo, calculating an expectation value requires 1 over epsilon squared samples. Amplitude estimation reduces this. The textbook one has a depth of 1 over epsilon as well, in addition to a scale. So if we give away some of that speed up, so if we say, we don't want a full quadratic speed up, we want something in between 1 over epsilon squared and 1 over epsilon, then can we use shorter quantum programs? So there's a few ways to do this. So my colleague Goldman, Paul Burchard, showed that if we can partition the problem into pieces that we can run in parallel, then you can do this. So let's say you split them. You basically take if you're trying to do quantum counting, you can take all the different pieces and run amplitude estimation on the little bits and then sum them up at the end. And each circuit will be shorter. So you'll run more of them. So you'll have more total samples, but each one will be shorter. But this requires you to know how to partition the problem into pieces, which we don't really know how to do in advance in derivative pricing, because there's some probability that your stock is going to go up and then come back down and then go back up, and we can't just sort of put you into bands. So working with some folks at QCware, Anupam Prakash and Jordanis Karanidis, and some folks on our team, we introduced two algorithms we call low-depth amplitude estimation. So the idea here is that you can pick some parameter beta and increase beta to change your depth, and also sort of basically decrease the depth that you run, but increase the number of total samples that you run. And so we get two algorithms for this. One is called power law amplitude estimation, which we had some smoothness assumptions that we had to make. The other is this algorithm called coprime, which uses some clever tricks related to the Chinese remainder theorem. And so you can pick betas with, for some integers, Q and K, and that allows you to tune between classical scaling and quantum scaling. And I think there's been some updates to this too as well. So if you want to think about this as a benchmark, then you now have a sort of depth-controlled amplitude estimation where you can ask for some hardware, what is the depth at which I stop getting useful sampling out of the sort of an advantage from sampling on the quantum computer, and I should stop at, so this, for some amount of noise that you have, there's some depth at which you should just start sampling classically, because if you keep adding more, you're going to get a bunch of noise. I think in the interest of time, I'm maybe not going to go through this in too much detail, but I'll sort of summarize that we worked with IonQ to start to run some of these low depth amplitude estimation algorithms on their hardware. And so what you're seeing let's just look at the bottom one here. What you're seeing here is just classical scaling, not of Monte Carlo in general, but it's classical scaling where we just take the oracle that we chose for this problem, which is the inner product estimation of two vectors, and we just ran that oracle at depth 1. And then we also used one of these sort of depth tunable versions of amplitude estimation and started to run that at different depths as well. And we were able to get a lower error rate, but it's sort of very, very barely visible on current generations of computers. But as we get more and more fidelity and more qubits, we'll be able to start running this benchmark and seeing, what's the depths at which we can get to advantage. If we can't get 1 over epsilon scaling, can we get 1 over almost epsilon, or even just a little bit better than 1 over epsilon squared as the fidelity improves. It's also worth calling out that there's a very recent paper by some folks at IBM, Rawl and Fuller, where they give a low depth amplitude estimation algorithm based on quantum signal processing that I think has the best constant factors of any of these algorithms thus far, and is worth checking out. Great. So we know that there's long-term valuable problems, but they have big requirements on the hardware. So what are the things we can do algorithmically in the near term to try and make the requirements on the hardware easier? Well, one is to have things like low depth amplitude estimation, where you can sort of tune the depth, and another is to start introducing software tricks and techniques around error mitigation. So I want to tell you a bit about this is 2 bits, a software package called Mitiq, and that helps run error mitigation. And secondly, a little bit of work that we've done using Mitiq to show some of the benefits for testing how to mix and match different kinds of error mitigating techniques. Great. So Mitiq is is developed by Unitary Fund, which is this nonprofit that Andrew mentioned. It's got like 50 contributors now, and there's not that many people that work at Unitary Fund, just a small handful of us. So I think that stands to it being relatively easy to contribute to and relatively easy to use. And the idea is there's a lot of error mitigating techniques that are out there, and I feel like there's a new one at least every couple of weeks or something on the archive, if not faster. And so as someone who wants to just run quantum programs, you are faced with a kind of daunting task to keep up with the state of the art in error mitigation. So wouldn't it be nice to have a package that lets you run like sort of relatively state of the art error mitigation with just a few lines of code for whatever program you want it to run? And that's what Mitiq does. And it's compatible with most of the existing software libraries. And this means like both front end and back end. So you can write in Circ and run on IBM, and you can write in Qiskit and run on Rigetti, and you can write in AWS and run on any of them. And you sort of have a front end and back end mix. So I think this package is especially important for two reasons. One is, error mitigation works to some degree at least, and everyone wants to squeeze as much performance as they can out of hardware. So let's try and make these great error mitigating techniques that researchers keep coming out with available to more people. But the second reason is for comparison and benchmarking. It's hard enough to compare hardware against each other or algorithm performance against each other, but now you've got this other independent variable of what kind of error mitigation did you use? And so it's nice to have sort of like a standard out of the box version. And obviously, if you want to tune it, then you can probably get better performance out of how you tune it. And that's why there's 50 contributors from people tuning a bunch of different things. So how does this work? And I think this is a decent framework for thinking about error mitigation in general. So a typical workflow in quantum software is you've got some quantum program that you've written, and maybe one of these or your favorite other one. Then you execute it on some backend, maybe one of these or one you have in your basement or lab. And what comes out is some expectation value. At the end of the day, the output of a quantum computation is some, we're classical people. It's some expectation value. So Mitiq goes kind of in between these two to help you run error mitigation. And a lot of, I'm going to hesitate to say all, but many error mitigation techniques fall into this structure. So you have some particular quantum program that you want to run. And what you do instead is you generate some set of intermediate programs that tweak or sample from or alter the original program in some way. Then you run all of those different programs on a backend or on several backends in parallel of different kinds. And you'll get a bunch of noisy results. And then you need, the second part of an error mitigation technique is how do you recombine those results together to infer some error mitigated expectation value at the end. Which is what Mitiq does. And in Mitiq, there's sort of a slew of different techniques. We're adding new ones. I'll talk a little bit about zero noise extrapolation and probabilistic error cancellation, which is like the quasi-probability method that Sergey Bravi was talking about. There's also clever data regression, and there's something called digital dynamical decoupling, which is a gate level version of dynamical decoupling that doesn't have an inference step. It just changes here. Okay. Great. And in case you needed more motivation that error mitigation is important to think about or interesting to work on, it's informed by a whole bunch of different work in a whole bunch of different related fields. There's open quantum systems and error correction, and then there's things about control and how do we do this with variational algorithms, and how do we characterize the noise, because some of the error mitigation modules are dependent on having a characterization of the noise model of your hardware. Some of them aren't as much. So it's a really, I think it's a rich area that's bringing together a lot of pretty cool ideas. So a very non-exhaustive overview. Some of these have been talked about already. So you have zero noise extrapolation, which there was some IBM work originally. The key idea here is if you can, you want to run your program at zero noise, you have some fixed amount of noise, but if you can increase the noise from where you are today, then you can back extrapolate down to zero. Probabilistic error cancellation is about decomposing your ideal operations into quasi-probabilistic representations of the operations you have, which are not ideal, and using that to produce the ideal ones. There's these sort of more learning-based methods where you're trying to generate sort of, I guess at a high level, you'd say you're trying to generate noisy outputs from a noisy quantum computer and use it to learn what the correct one should be. There's sort of symmetry based techniques. There's things like dynamical decoupling and randomized compiling, where you're trying to change the noise model by inserting gate sequences, let's say for dynamical decoupling, to protect from bad noise when you have idling qubits, or by inserting random gates to try and transform your model to be like more depolarizing, because that behaves better. And there's been a bunch of work in this. Pretty much, wow, like almost a lot of this is really just in the last couple of years, but often pulling on ideas from quantum control that are much older. And so I'm not going to pretend to cover all of this here, but I just want to point out there's a lot to learn and see. And even some reviews, including we recently put out a paper where we did some cross-platform benchmarks of PEC and Z&E just about a week ago. And if you want to learn more about this stuff in practice, then Mitiq's documentation can take you through it. And to the extent that we have code for it, which is we do for sort of these four, then you can try it out too. So as I mentioned, Z&E is about taking you have some noise value on your hardware. You want to increase that noise value somehow, and then extrapolate back to what the expectation value you measure would be at some zero noise limit. And so there's two main parts to this. There's how you're going to do the scaling of the noise. And then secondly, how do you fit that noise to extrapolate to the zero noise limit? So there's kind of two choices for how you do that. So in Mitiq, the flow is you take some quantum program, generate these noise scaled circuits, run them, fit a model, and infer the zero noise level. So there's sort of like maybe two categories of noise scaling methods broadly. One, there's analog ones, which were used in the original Z&E paper, where what you can do is take the pulses on your hardware and make them longer. And so if there's noise, then you'll accumulate more of that noise because your operations are taking more time. So that's called like an analog method. And then there's digital methods, which we call sort of these unitary folding ideas, where you take some gate and you replace it, append to it G dagger and G. Logically the same, but longer. And you can do this at API level, an open chasm level, not needing to recalibrate any pulses. So think of it as like the platform independent version of noise scaling. And there's a bunch of ways of doing this folding in Mitiq. There's local folding where you replace each gate. There's global folding where you fold the whole circuit. You can do this to integer multiples, but then if you need to get to, let's say, 2.5 folds, you then like randomly subsample parts of the circuit to fold. You could also choose to fold particular gates. So just fold the C naughts. If you think that the single qubit gate errors are not so important and the 2 qubit gate errors are important, you can configure that. There's a bunch of flexibility of how to do noise scaling, and you can introduce your own. The second part is how you do the inference. So you can do, so these are some plots on one IBM processor, one on Rigetti, where we're looking at some randomized benchmarking circuits or sets of randomized benchmarking circuits and scaling the noise and then inferring back according to several different models what the zero noise level should be. There's linear methods, polynomial methods. We call them factories in Mitiq. You can also think about doing this more adaptively. So this adaptive factory is where the noise scale factors are chosen adaptively. So instead of saying at the beginning, I'm going to sample 1, 2, 3, 4, 5, 6, 7 points at these noise scales, you can measure for a while, then choose a new noise level to scale at, then measure for a while, then go somewhere else, then measure for a while, and sort of more optimally do this adaptive exploration of this trajectory of the observable for your noise scale. And Mitiq's Zeni is probably the relatively straightforward technique to use, partially because you don't really need to have a characterization of the noise model to just try it. So it's pretty easy to run a couple lines. So it's been used on Rigetti programs through brackets. So this is it should be one. So without zero noise extrapolation, with zero noise extrapolation, it's improved. People use it for quantum field theory models, and you can even use it to do things like measure quantum volume, but with error mitigation on top, which we call effective quantum volume, because it's a different benchmark, because you're now allowing yourself access to the classical resources to improve quantum volume, which is different than just running on the raw hardware. But on a couple different smaller IBM processors, we were able to add a couple points, 3 to 4, 2 to 3, 3 to 4, 4 to 5 quantum volume by using ZNE for this effective quantum volume metric. And I think what I'll say about, so I like this effective quantum volume work quite a bit, mostly as a way to compare error mitigation techniques against each other. So you could say that, my implementation of ZNE improves the effective quantum volume by 2 and yours only does by 1. So like maybe my error mitigation technique is better. It's not really exactly the same as having a quantum computer that is that much better. I think in the interest of time, and because it was in the last talk, I'm not going to spend too much time on PEC, but this is another really interesting technique for probability method for estimating expectation values. Similar to ZNE, it's got this kind of framework. You take your quantum program. In this case, you're probabilistically going to replace gates in your circuit. Then you're going to execute them all, and then you're going to reassemble them at the end. And here you do need to have a noise model. Oops, skip that. And so, but I want to tell you a little bit about kind of another thing that you can start to think about doing when you've got error mitigating techniques into a software package. And well, one thing you can do is they're complicated, but you can just compose them. You can say, well, why don't I, every time I generate a noise scaled circuit for ZNE, why don't I run PEC on that and see how that works? So something kind of in this vein, but more theoretical level, is called noise extended probabilistic error cancellation that I worked on with Andrea Mare and Nathan Shama at Unitary Fund. And so the idea here is that in probabilistic error cancellation, you, at some base noise level of the hardware, you pick different circuits to run where you're replacing gates probabilistically. In zero noise extrapolation, you're taking the same circuit, or at least the same logical, really logical circuit, and running it at different noise levels. And so you could imagine this noise extended framework where you give yourself the freedom to do both. So you can scale the noise, and you can also change the circuit. And it's not that there's an implementation in our research repo about Mitiq as well. It's not entirely in Mitiq yet, but if you want to contribute to GitHub and contribute to Mitiq, we'd love some help finishing this up. Oh shoot, I'm missing a slide. Oh, I missed the results slide. So let me tell you the sort of takeaway result from this NEPEC technique, which is that if you use NEPEC compared to normal probabilistic error cancellation, then you can get a version of error mitigation that is more robust to errors in your characterization of the initial noise model. So when you run PEC, the first thing you need to have is a noise model representation of your device. And device parameters change over time. You might just have, you ran some characterization routine that has some error.
50 years old.
Oh. So it might have some error in the initial characterization. And so if your error, if you've made a mistake in how you characterize the noise model, then the probabilistic error cancellation on top will not perform as well. However, if instead of using vanilla PEC, you use NEPEC, you can become more robust to mistakes in your original noise characterization. So there's more types of things people have used Mitiq for. So I mentioned a few of these. protein folding, correlated materials. The point is to help save you some time in implementation. And if you're interested in that, feel free to reach out. So I think with just the last couple minutes before questions, I'll just mention an area that I'm pretty interested in, but I'm not sure where it's all going to come out. I mean, Sergey talked about this work just before me in particular. So I think, it's not likely that we're going to have a step change where all of a sudden we turn on error correction and now all of our qubits are perfect. It's going to be a sort of like a smooth process where we start to introduce error mitigation in different forms, other things like entanglement forging or circuit knitting or small depth, small distance codes of different forms, and they all need to sort of mix together in some interesting way. Having good implementations in something like Mitiq can help you mix and match these things heuristically and numerically, though of course there's lots of room for good analysis. And so I think this sort of intersection between error mitigation and fault tolerance is very interesting. And then just quickly kind of about Goldman's side, we're working backwards for quantum advantage and concrete problems, and always looking for partners and collaborators. And also, resource estimation is hard. Constant factors are fiddly. We're doing things like figuring out, the number of C naughts in like floating point and fixed point quantum registers, register arithmetic, and having better tools to help us do that would be really helpful as well. Thanks.
Great, thank you, Will. Thanks for the great talk. Again, so if anyone has questions, please raise your hand and let me know. Yufei, would you like to go ahead?
Yeah. So I have one general question. So it seems that it's very interesting, especially to say how quantum computing can potentially benefit this kind of finance applications. And if we look at the speed up, it's mostly quadratic speed up. Do you think there is a way, for example, to reformulate the problem and search for new quantum friendly algorithms that could potentially give us quadratic exponential speed up? Yeah, from the algorithm application code design perspective, especially now we have better understanding of the hardware from the hardware model and combine the specific characteristics in the application. Do you think there's a way there? Yeah.
It's a great question. I think I have it on here too. We're very keen for super quadratic. It doesn't even have to be exponential, but super quadratic speedups. There's some stuff around, there's differential equation-y things. There's maybe some optimization stuff that's not likely to be exponential, but maybe it's linear or super quadratic. There's some recent papers about topological data analysis where people sort of go a little bit back and forth. I don't, if I had this is a big valuable exponential speed up in quantum finance, and here's how we can do the resource analysis. If I had that would be probably most of my talks.
Ask that question because I feel that, if you look at the finance applications, I guess a lot of things are related with how people think, right? There could be some hidden structure there. I don't know. I just feel like human beings sometimes look very like qubits. That's my perspective. Yeah, if we can really see the insights behind all this kind of finance behavior, maybe we can do something really interesting. I don't know. But yeah, very interesting talk. Yeah, thank you.
It looks like we have another question from Ivan. Okay. It's posted in the chat. I don't know if you want to unmute and ask your question, or I can read it. That's fine.
Really quick, are they always diagrammatic? Do I need category theory to use that ever?
I think I'm not quite sure I understand the question, but yeah, I'm not sure. I don't think I understand. Could you say a little bit more? maybe they're.
For example, in Lisp code, you do need it, and Scheme, you have to use it. For example, physical errors can occur with respect to physical noise radiating from such a qubit, or any sort of n number of or quitrit or quit-it, whatever. It's just a general question as to error mitigation for physical qubits, or physical ions, rather.
Sorry, but I think I might have missed the question part. So your question's about how errors work on different qubit systems. What's the you're asking?
As opposed to interfacial logical qubits. But what about like the physical ones?
Yeah. I mean, so physical qubits often have more sophisticated kinds of errors than what we model when we're doing our theory, either for mitigation or error correction, unfortunately. So one of the things that is not necessarily modeled all the time are the effect of correlated errors. So if I get errors in one set of qubits, how does that correlate in space or time with errors in other places? And that can really affect the performance of error correction. And it can also affect the performance of error mitigation. So I actually have a paper where we look at the effect of time correlated noise on zero noise extrapolation, and actually some ways you can use zero noise extrapolation to try and deal with time correlated noise. I'm not exactly sure if that's the full question, but I suppose that's what I can what I can say about that.
No, thank you. If you could send the link in the chat or something, I'd appreciate it. I'll read it. Thank you.
Right. Are there other questions? Because question from Abhi.
Hi, can you hear me?
Yes.
Mm-hmm.
Hi, thanks for the great talk. For error mitigation, you cover like ZNE and like PC. I'm wondering, like you briefly mentioned, there's like kind of learning-based approaches where people are applying like technologies from like machine learning. I'm wondering like if you have more insights into that, like how actually that's being done.
Yeah, so it's probably more than I can cover in a couple of minutes, but I can point you to a few places. There's a technique called Clifford data regression, and in the Mitiq docs, there's some links to papers. We didn't come up with that technique, but it is implemented in Mitiq. And sometimes, like one example of something people kind of can try and do is to find a circuit. So you're trying to run some quantum program. I want to find the Clifford circuits that are close to that program. And Clifford circuits are efficiently simulable on classical computers. And so maybe there's some way I can run those and then combine them to get an answer to the program I actually wanted to run. And there's other versions of that. But I think I'd point you to the paper list in Mitiq. Yeah. And there's lots more to figure out there, I think.
Great, thank you.
Yes, Will, I have a question. In the first part of your talk, you looked at implementations of algorithms, down to the gate level. And I was wondering what the implementation of those applications teaches you about how to organize a fault-tolerant computer. Like if there's some insight as to the preferred gate set, or how to use, like what parallelism is there and how you might exploit it, or what it says about throughput of resource states, things like this, to kind of move toward more interaction between computer fault-tolerant architecture and algorithms.
Yeah, that's a really, really good question. And I wish I could give you a really, really good answer. Those estimates, we've so far mostly done estimates at that logical level. We said it's Clifford plus T, and like, let's count Toffolies and T gates. I think, one thing that definitely comes up is that for these kind of applications, probably for a lot of the quadratic speedup applications, like a single T factory is going to rate limit you really aggressively. We, in the resources I gave, we optimized for T depth mostly, not everywhere, because sometimes there's really bad trade-offs, but like the broad desire was to optimize for T depth, and that's just because we knew the clock rate demands were going to be extremely high. And Yeah, I mean, if you have a single G factor, basically if you can't run T gates in parallel, you're going to be in real trouble. I think people probably already knew that, but I think there's more follow-on work to be done, and we're trying to do some of it to take the implementations all the way to the physical level, and then start to look at layout and stuff like that. If people want to collaborate on that, I'd be super keen to talk about it.
All right, great, thank you.